growth and decay. In this section, we're talking about growth and decay application problems. Now we have an exponential function. All you look at is the base right there, and that tells you if it's a growth or decay function. Well, for the most part, a growth function is when the a is greater than 1, and decay function is when the a is less than 1. So let's look at 4 examples. A scientist monitoring a grasshopper plague notices that the area affected by the grasshopper is given by this. So this is the area affected by the grasshopper in hectares, where n is the number of weeks after the initial observation. So n is weeks after observation. So find the original affected area. So anytime they want the original amount or the initial amount, then that's just when our independent variable is equal to 0. So in this case, when n is equal to 0 is our initial amount. So you substitute in 0. A of 0, which is my initial, equals 1,000 times 1.15 to the 0 power. That just equals 1. So 1,000 times 1 is 1,000. So 1,000 hectares is the original affected area. B is find the affected area after 5 weeks, after 10 weeks. So for B, we're just going to substitute in A of 5. Use that, I'll put that into our calculator. So here we go. So 1,000 times 1.15 to the 5 weeks, and I get 2011.4 hectares. And then A of 10 weeks, after 10 weeks, so I'm going to go up here and select my same problem and change the 5 to a 10. And then we get 4,045.6 hectares. So that's A and B. Draw out the graph of the affected area over time. So we use a calculator to do that, but honestly, we're just going to do it by hand real quick. So we should know how to graph these. Right, if I'm looking at this, and there's no horizontal asymptote, right? There's nothing there, so 0 is my asymptote. And then remember what that is? My A is my initial y-intercept, so I'm going to go up to 1,000. It's my initial y-intercept, so it's going to look kind of like this. And it keeps on going. Use your graph or technology to find how long it would take for the affected area to reach 8,000 hectares. So all they want is our equation, which is this, to equal 8,000. You could use our graph, which our graph's not nice enough to graph to use it. So I use a calculator to solve this. We'll do the same way. We'll type in y1 and y2. So I already typed in y1. Y2 is going to be 8,000. Remember, we've done problems like this before. If I'm going to graph this, I'm not going to be able to see anything unless I change my window to see the 8,000. So I'll make my window go all the way up to about 9,000, so I have some wiggle room to see. Now let's graph it and see how it goes. Alright, so we're going to graph this. That's the first thing you're going to see here. And then we're going to cross it. Then we're going to graph 8,000. And that, so you have to fix your window. If you have to make something bigger than what your highest value is. In this case, 8,000 is my highest value. Maybe my window 9,000, I could see the intersection. So second calculator, intersect. I want to kind of get close to the intersection points around there. Hit enter a couple of times. I guess, yes. And we're going to get 5.128. So I would draw the picture. I'm going to kind of drew it. Right there is n equals about 5.128. So it'll take about 5 weeks. So a little more than 5 weeks. Okay, next problem. A species of bears introduced to a large island off Alaska where it previously had no bears. 6 pair of bears were introduced in 1998. It is expected that the population will increase according to this metric here, where it's t number in years since introduced. Find B0. Well, B0, if you look at our equation, is our initial amount. So it's our initial amount. Well, they told us 6 pairs of bears. So is this pairs? This is a population of bears. So B0 is going to be 12, right? 6 pairs, so 12 bears total. Find the expected bear population in 2018. So they introduced in 1998. 2018 will be 20 years later. So all I'm going to do for B is we're going to figure out B of 20. So it'll be 12 times 1.13 to the 20th power. I'm going to type that into our calculator. Come on, move with me. There we go. So we're going to get 12 times 1.13 to the 20th power. and we get about 138.27 bears. So if I was rounding, probably 138 bears would be my expected population. We're talking about number of bears. Find the expected percentage of increase of population from 2008 to 2018. So percent increase, this means I want my population from here over the population from there. So I gotta find the population in 2008. So let's find population after 10 years. So let's find that first. So I'm gonna go up here and select my population, change that 20 to a 10. And I get about 40.73. And then the expected percent increase, you just go the number in 2018 over the number in 2008. So 138 over, let's say, 41 bears. So I was thinking of this value divided by this value. This would be my percent increase. Which would be about 339% increase. And then, so that's my percent increase. How long would it take the population to reach 200? So I'm going to set the equation up to 200. We want to figure out when 12, 1.13 t equals 200. Now, again, as of right now, we haven't figured out how to solve this yet. That's going to come up in the future lesson. So the only way I can do this is by doing y1 and y2. y1 is 12 times 1.13 to the x, and then y2 is 200. Then we're going to fix my window so I could see it. I don't need to go all the way to 9,000 anymore. I can go to like 300. It's not even something more than 200. So there's a graph, and it looks like that's going so slow. I might have to fix my x. Yeah, let's fix my x. So we're going to negative 10 to, let's go negative 10 to like 100. Let's go 100-year span here. And it looks like I don't get as hard as 200, but let's see where this crosses. Up there. So second, calculate intersect. And we get it takes about 23 years. So there we go. So about 23 years and take population to reach 200. Next one, let's do decay graph. How do I know it's a decay? Because look at the value right here, right? This is my decay value. So it's less than 1, so it's decaying. Right here, population was greater than 1, so it's growing. Population is greater than 1, so it's growing. Let's do a decay problem. A diesel electrical generator switched off, the current dies away according to the formula of this amps. Proceed time to seconds cut. Find I of t when t equals 0, 1, 2, 3. So all we're going to do is substitute in 0, 1, 2, and 3. I'm going to skip that to put in your calculator. What current flow is generated in the instant to turn off? So that's the one I'm going to do. So this is where t equals 0. Again, A, all you do is substitute them in. Right, that's all you do for A. Plug in 0, 1, 2, 3. I'm going to do it here for B, so same idea. When it's instantly turned off, so that's when t equals 0. So 24 times 0. 0.25 to the 0, that's 1, and you just get 24. So 24 amps, we're talking about amps here. C, plot the graph of I of t for t greater than 0. Use the information above. So, we could use a calculator for doing that. Or if we did all the work in the first one, we could use those points. But we know how to graph this. We have 24 times 0.25 t. So I know it's plus 0, there's no horizontal asymptote. So horizontal asymptote is y equals 0 because there's no vertical shift. I know my initial y-intercept is 24, so we'll hit at 24. And I know that's a decay because this is less than 1, so my graph's going to be going down. So it looks something like this. And this is just a sketch, and we cannot go past the asymptote. So that's what my graph looks like. That's C. D, use your graph or technology to find how long it takes for a current to reach 4 amps. So all we're going to do is graph 4 amps and see where they cross. Now again, it's not a perfect graph there, so I'm going to use my calculator again. Bring that back up here. So y equals 24 times 0.25 to the x power. and then we want to hit 4 amps. Let's go back to zoom standard, zoom 6, to see what that looks like. So there's a decay graph, notice it's going down, and then there's across this, so I gotta figure out that value. Second calculator intersects. First curve, second curve, and then it finds it right there. It's 1.292. So right there for D, it is T equals 1.292. That's how many seconds it can take for the amp to hit 4 amps. That's pretty much it. Let's look at this last one. I'm not going to do the whole way, but initial count of orangutans in the forest found that the forest contains 400 orangutans. Since then, the destruction of their habitats caused the population to fall 8% each year. I actually am going to do this one. I realize this is a little bit different. Write a formula for our population. So our general formula for our population is y equals a b to the x, like the general initial growth or decay graph, something like that. Now we start with 400 orangutans. That is our initial amount. That is our a. And then it falls 8%. So that's very important. The way you find your b, it's 1 plus or minus r, what the rate is. So in this case, it's falling 8%. So it's going to be 1 minus my rate, which is 0.08, because it's 8%. So my b here is going to be 1 minus, because again, it's falling to decay, because the growth would be plus 0.08 rate, which is 0.92. So this is going to be our general equation for a. Y equals 400 times 0.92x. So there's our equation. Find the population ranking after 1 year. So my population after 1 year, just substitute in 1. 400 times 0.92 times 1. Let's put that in the calculator. 400 times 0.92 to the first power, you get 368. After 5 years, let's go back here, now I'm going to put it to the fifth power. I get 262. About, approximately. 263, I should say, and 64, rounded up. Sketch the graph of the population over time. So again, you can sketch by hand or the calculator, but we know how to do by hand. This is my, I don't have a Virgo shift, so it's plus 0. My initial point's going to be right there, 400. And it's a decay, so it's going to go down like this. You don't go past the asymptote. So that's that effect. Figure out how long it takes the population to fall at 200. So we want to know when this guy equals 200. That's to be y1, y2 in our calculator. So we're going to get 400 times 0.92 to the x. And then we're going to go 200 down here. Again, fix my window. Right now I can't see 200, so I'm going to go all the way up to 200. So I'm going to go to like 250 on my y. Let's expand the max a little bit. Let's go to like 50. Give some time for them to fall. So again, first you should see your decay graph. Again, notice how it never goes past the asymptote, and then you have your 200 right there. So let's figure that out, what that value is. And our intersection is going to be at 8.31 years. And there we go. That's the lesson.